everybody to the November FPGA seminar, and it'll be given by Alex, who is a PhD student just about finished of Jonathan Rose. Take away, Alex.
Okay. Right. So I'm here because I like to build hardware using FPGAs, and as I've been doing that over the years, I have used lots of tools to help me do that, and I have had good experiences and I've had bad experiences. So I decided to make my own tool to help me make my designs and turn that into a PhD thesis. So it's been a long time since I've given a talk here at this FPGA seminar about my project. So part of my talk, the first half of my talk, is going to be me getting new people up to speed and sort of helping give context about this tool. For the second half, it's going to be a deep dive into whatever the meat of what I want to talk about today, which is the automatic pipelining features of my tool. So just to give some context of what space we're working in, when we design for FPGAs, we have many tools and technologies available to us. Of course, there's always writing directly in Verilog, which we want to now avoid as much as possible. And different people have taken different approaches to helping us do that. We have HLS tools, which take the more behavioral route, so you can code in a more software-like language, like C or OpenCL, and that will turn that into hardware for you. So this is pretty attractive for people who are used to software because it's behavioral. And there's another class of tools that maintains the structural spirit of hardware design, and these are the system building / interconnect synthesis tools. And every vendor kind of has one. Altera / Intel has QSYS, now it's called the Platform Designer. Xilinx has part of Vivado that does that, and I think Lattice has, the other guys have their own thing. I don't know what's going on there, but I know they have something too. So my tool that I'll be talking about lies within this space. The system building tools, this is a general way of how they work and what inputs they accept. So because it's hardware-like, you still have modules. You still have this idea of functional modules. I call them functional modules to distinguish them from automatically inserted modules that the tool itself will then put in to glue them together. So these are made by the user, and they're made using one of the methods that were listed before. It doesn't really matter. So to get the tool to do something with these, create one or more interfaces on each module. And these interfaces conform to some protocol that's known to the tool. Usually popular standard protocols include AMBA, AXI. So these interfaces are essentially higher level groupings of HDL signals that work together to send data across this interface. The user then defines one or more logical desired links between these interfaces, tells the tool I want these interfaces to communicate. And these represent kind of fatter, richer, with more semantic meaning connections than just raw wires. And nominally they're directional, but they could be essentially do bidirectional data transfer. So if you have like a master and slave arrangement in a SoC, when you do a read, that involves both a request and a reply. So there's a lot going on in these logical links. You're asking for a lot to be done. This is the higher level aspect of these tools. So what the tool does, after you give all these inputs, is it creates a system that instantiates the modules that already existed, and it turns those logical links into physical interconnects. I'm using the word interconnect in this talk. I don't mean the wires inside the FPGA that like an architect would care about, the low-level wiring and the switch blocks and all that stuff. No, this is soft interconnect that's made using logic, and essentially this tool, it relays this as Verilog, which then goes to a proper CAD flow. So that's the final output of these tools. So I said these tools exist. What are some of the limitations that I've seen that's out there? Well, the main thing is that, I guess, due to market demand and how engineers use them, mainly these tools existing tools are designed around an SoC mindset, system on chip, where you have one or more software hard processors kind of dominating the system, and they're talking to some memory map peripherals or IP cores. So everything's been kind of designed around that use case. And as a result, the interface protocols that I talked about in those interfaces, they use mostly memory map protocols, which is great if you're building it for the use case that I talked about, but if you're not, then you kind of have to finagle your communications to look like memory map reads or writes. or just go back to doing everything by hand, which you don't want to do. Yeah, so memory map's not a good match for some types of communications. So for example, it's lacking the ability to do things like broadcast or multicasting. You just can't do that with memory mapped addresses. So besides memory maps, streaming protocols are also supported by these tools, and these are point-to-point connections that are lower level and make fewer assumptions about the communications than memory map does. But they come with a low level of automation. What I mean by that is when you specify that streaming link, nothing much is done by the tool. It's just a point-to-point connection with wires is what you get. You don't get any ability for the tool to instantiate interesting interconnect to do that. So that's a trade-off that you have in this current world. In addition, the interconnect that is, if interesting interconnect is generated through these memory map links, it's not, what's in commercial tools is more basic than what's been covered in academia and research. So we have networks on chips. We've been studying these for decades, and there have been lots of papers and architectures and even tools to generate the networks on chips themselves. But where are the full system end-to-end tools of the nature of like QSys and Vivado that build SoC type things where you can customize the topology and choose how the data is shared between physical links? And because of the simple interconnect, you don't get much opportunities to really optimize it because there's not many degrees of freedom. So that's the existing world that I saw before I embarked on my project. So now I'll talk about a tool. It's called Genie, the generic interconnect engine. So like the tools I've been talking about, it's a complete end-to-end system building tool. It will create a system with your functional modules and the interconnect that it generates. And it aims to generate fast and lightweight interconnect, which will make it more usable in situations where previously a tool like QSys would create too much overhead, area overhead to be usable in those situations. It's what I call the fine-grained world as opposed to the coarse-grained world. The inputs and outputs are of the same nature that I've talked about, but in Genie they are provided via a script rather than, let's say, an XML file. This provides some interesting capabilities for automation. So Tickle exists, it drives a lot of tools. I chose a scripting language too, but it's not Tickle, it's Lua. I like it better, it's cleaner, maybe some of you will agree. And through the script, programmatically, you define all the inputs I talked about. You define your functional modules, including the interfaces. You define the system that contains instantiations of those modules and the logical connectivity between them. And also you're able to provide additional metadata like constraints about those links, about the system, about things you want to desire to be done to control the tool. And as output, it generates synthesizable system Verilog for each system, as I showed a few slides back. Well, next few slides, we'll go over in detail some more of these inputs, just as a more overview and some of the Genie-specific things that it does that other tools don't. So some of the features that Genie has, I've been adding them over the years, writing papers about them, and giving talks at conferences. Basically, there's a lot here, and I'll only be talking later in the second half of this talk about two of them, which is the automatic interconnect pipelining and synchronization of fixed latency modules, which is something that's actually been presented before, but these two bolded things are very much tied together, as I'll show you, and it's best to solve them together. And on the idea of togetherness, each of these problems has been studied in academia before by others and kind of in isolation, but the trick and the challenge is to creating a full tool is to get all of these different algorithms and optimizations and automation features to work together cohesively, and sometimes in imperfect and ugly ways that us engineers have to deal with. So that's been one of the challenges of this project. Okay, so back to Genie and its inputs and outputs. This is a pictographic representation of what I showed before. You have a script written in Lua that has all the inputs I talked about, and it goes into the tool, which is an executable. Genie also maintains a database of a few interconnect primitives, which it has the Verilog for. And this outputs this system. Meanwhile, the user has implementations for the modules that they talked about. Genie doesn't touch them. It just needs to know about their interfaces via Lua. At some point in the future, it might add features. No, I won't. I need to graduate. But at some point, somebody may. It's possible to add a feature where it will automatically look at the Verilog and extract some of the interfaces, so you don't have to repeat and keep them in sync. This laser is not being lasery. There we go. So that just stays as it is, but the system instantiates your primitives and instantiates Genie's primitive and instantiates your modules to make up the system. And Interconnect is just made of a lot of instantiations of the primitives. Detailed look at some of the inputs. They're modules. You built them using some method. They each have one or more interfaces, which themselves are groupings of HDL signals. And each of these interfaces has to conform to some protocol. So there are multiple types of supported interfaces. So I want to talk about some of the protocols that Genie supports. Genie has 4 interface types, and I built this a lot around existing tools of this nature that are commercial tools like QSYS. There's utility interfaces like clocks and resets. They just have a signal, but I need to know that this is a clock, this is a reset, because there's associations made with other interfaces to tell me like what clock domain is this on. Yes, I like to support real things like designs of multiple clock domains, because real designs have that. In addition to clocks and resets, there's conduits, which are just a bundle of untyped signals that Genie knows nothing about, doesn't want to know anything about. It's just like QSYS's conduits. It just connects them to bundles together with no automation whatsoever. So if you have like an off-chip memory controller that has very exotic signals or some IOs, export it as a conduit and leave it alone, because you don't want it to be touched. So one interesting interface type that I have, I call it the routing streaming interface. So when you make logical connections as a user between routed streaming interfaces, that's when Genie will actually generate interesting, rich interconnect to realize those links. And routed streaming protocol, which we'll talk about more in the next slide, is inherent to unidirectional. So memory map stuff is bidirectional. This assumes a lot. I mean, when you do reads, that is. But because the streaming part of it, protocol I'm about to talk about, is unidirectional. So you can do the most possible things with it by just using many interfaces. So when I was designing the RS protocol, my goal was to have minimal assumptions about what this is going to be used for. So memory maps, like I said before, the limitations of that is you can only express everything as reads and writes. So I want to avoid that world where I'm boxed in into a specific use case. So existing streaming interfaces and other tools do this, but they don't have the automation capability that I want from the tools. So in addition to having minimal assumptions, I still want the tool to be able to create lots of rich automation around the logical links that you define. So the nature of the RS protocol, it looks like a regular streaming protocol. Yes. Plus an address signal that tells it stuff where to go. That's also multicast capable, so it's as general as possible. Anything you build with this should be able to be built. You should be able to express the same range of things that you could when you write pure Verilog, meaning a wire can be broadcast multiple places. That's easy, but memory map can't do that. So I want to be able to recreate the broadcast capability when you need it. The signal roles that comprise this protocol are, I try to keep it minimal again, minimal assumptions, and you just design it to answer basic questions about your communications. There is a data signal. You can have multiple data signals of arbitrary widths and multiple named channels that all match up when you connect the interfaces together. There's handshaking, valid and or ready signals that are optional. There's an end of packet signal, just like I guess Avalon streaming. That's where I got the idea from. That just lets you dynamically specify how long your transmission is, and your desire to keep that unbroken as it's being received. So no other transmission will interrupt and multiplies the sway when that happens. Ooh, slide 12. Okay, so, and there's an address signal, which, like I said, is not memory mapped, it's just an integer, but it's also multicast capable, as I'll show. What I try to do is make all of these optional. So even data is optional. You don't need a data signal. You can do interrupt-like communication that says an event has happened. You don't really need any data with that. And so I think pretty much every combination of these is optional. If you have no address, then all the links you make, it's going to be broadcast. So that's kind of my goal here, maximum flexibility. Okay, so if you define your modules and your interfaces, which the RS ones are the interesting ones. You define your system, which instantiates the modules, and create logical links between the interfaces. I'm only showing routed streaming interfaces here because those are the interesting ones. So you define links, and optionally, you can also, this is when you assign addresses. In Genie, addresses don't belong to a destination. They actually belong to the link. I'll explain that, and that's what lets me do multicast. So for example, here I have a module instance A1, a module instance B2. They each have one interface, one source, one sink. They're connected via this link here. This link has a source address of 1 and a destination address of 0. And what that means is, when A1 drives the value 1 on its address port, they will activate this link and send it to B2. So that's how you choose destination. Meanwhile, this destination address, which doesn't even have anything to do with the source address, means when B2 receives this transmission, it will see a value of 0 on its address, which will let it know where it came from. So the cool thing I wanted to add is for destinations to know where it came from. That's not something you often see in the existing protocols. An address is something you send to, but it's not really ever been, you know where it came from in a way that's independent. That can change on a per link basis, meaning these numerical spaces of addresses are not global, they're local to a link and can be made as convenient to the module designer as they want to be. How multicast is achieved is actually pretty simple. Instead of having 0, 1, and 2, imagine these were all 0, 0, 0. That's allowed, because those zeros belong to the link, and all these 3 links can have a 0 source address. If that were true, then when my send interface here drives a 0, it will simply broadcast it to all 3 of them. And you can have some combinations like 0, 0, some other number, and multicast the sum of them. So via this addressing scheme, I can implement multicast and broadcast as well as unicast transmissions. Okay, I want to talk now more about the actual interconnect that Genie builds. Again, I had a design goal when designing the interconnect. The second half is I'll be talking about the register insertion phase of this interflow, which does the 2 related tasks of automatic pipelining and synchronization, which I will talk about what that is. So why would you ever want to insert registers? Well, I can think of 2 reasons in hardware. One is synchronization, where you want to add registers to add cycles of delay intentionally for the purpose of functional correctness and aligning data. Second reason is for pipelining, which you want to add registers to break up combinational paths because you want to increase clock frequency, not for correctness, but for performance. So 2 vastly different reasons for doing this. And these directly correspond to the 2 steps that I'm going to be performing. Because they both insert registers for different purposes, these problems are dependent, and it's best that they're solved together, which is where this is going to be leading. And I will now talk about each problem separately. But before that, and time permitting, yeah, we're good. Quickly review the process I'll be using to solve this. The optimization technique is called ILP, interlinear programming. Many people know this. I didn't when I started, so it might be a good time to just refresh for those who don't. Basically, it's a way of solving series of equations that are linear, not actually equations, they're inequalities. So they're linear equations of certain unknown variables x with coefficients, and there's a relation operator and there's a constant. You have many of these constraints, these equations, and the goal is to find a legal solution that satisfies these constraints, while also trying to maximize or minimize some goal function that's also a function of the unknowns. That's also linear combination. So that's what it is, and Genie uses the ILP solver called LPsolve to kind of download and outsource the solving to that library. So the big picture of the whole register insertion flow and where these 2 different processes fit in is like this. We first start with a register-free netlist that's unpipelined. It will look like this. We have a register-free netlist, we insert registers, now we have registers. So to get there, the register-free netlist is examined by these 2 independent processes, synchronization and pipelining. They output their own ILP constraints to an ILP solver, which then solves for the number and location of registers to insert on every unpipelined physical link. And then that drives this register insertion. So first, let's talk about synchronization and provide some motivation for this. So imagine the following situation. We have 4 modules, A, B, C, and D, and these are fixed latency modules, kind of like a DSP application, where you have a known input to output latency of some clock cycles. B has a 2-cycle latency, C has a 4-cycle latency. And there's different data widths for inputs and outputs. Everything reconverges at D. Now, in this application, this mini application, we really want D to get its inputs simultaneously, despite there being different latencies. How would we do that? Well, if we're building this whole system with an interconnect synthesis tool, we provide the modules, but we don't build the interconnect. We just provide logical links. We don't know about the implementation of what interconnect is going to be along these links. So one solution, one easy but not good solution to synchronize, is for us to control what we can control, which is the modules. So D becomes D prime, and in it we stick some FIFOs to help us manage the delays. And then we will DQ together from these FIFOs so we get the synchronization. This will make our design independent of the interconnect design and latency. But it's not ideal because we have these FIFOs here. That's more than what we need to make it happen. In an ideal world, however, if we had full control of the interconnect and we wanted to spend some extra effort to do this right, we would do this instead. So I'm using orange to mean manually created links, blue to mean automatic made by a tool. So now we create everything manually. Instead of using the tool to build the interconnect, we have full control over it, and we can insert registers into the interconnect to balance the delays ourselves. And there's many possible ways to get a correct solution. We know we need 2 registers after in the B path to balance the 4 registers for C, but there's many places to do them with different costs. So if we put the 2 registers after B, that will cost us 512 total flip-flops because of the data width. There's a better solution, of course, to put 2 registers before. It'll cost us 18 registers. So this is great, but the problem is we now have to spend the effort to not only make this ourselves, but also choose among many different possibilities that are legal to find the one that's least cost. So the goal of the cycle-accurate synchronization feature of Genie is so I can live in a world where this best solution, instead of being manual, is automatic, because it's blue now. And the best solution is found and created by the tool. So to make this happen, Genie needs some new inputs. One of which is internal links, which just, before we had logical links between modules, now we need internal links within modules that say between some input interface and output interface, what is the fixed latency. And then to express our desire for synchronization, to express the relationship that stuff must arrive at the same time at D, we have these actual synchronization constraints. So these are relationships between paths called chains, which are a bigger version of logical links. So a single logical link is like this between 2 modules, but we need to be able to express a path from module to module through modules from an initial source to a destination. So that's what a chain is. And in this case, we have 2 chains and we want the delay to be equal. So the synchronization constraint in this case to express this desire will be the following. Latency of chain 1 minus latency of chain 2 equals 0. To the user, this is what they would look like in general. We have 1 or more chains related by some sum or difference of the latencies, an inequality or equality operator, and an integer constant. And the possible uses of these constraints would be simultaneous arrival of data, like I showed. Also, sometimes you want non-simultaneous arrival of data, because you want things to arrive in kind of a non-overlapping fashion. Or bounding some round-trip path, which is the sum of some forward path and backwards path, to be less than something. Because let's say you have a FIFO that has like limited capacity, and you want credits traveling backwards and forwards, and you want things to fill up just the credit return to happen just as it fills up. So there's many applications here for latency-sensitive communication as well. So those constraints are what looks to the user. This is what Genie does with them to create a required output to solve them, which is ILP constraints. It's pretty straightforward. 1 user synchronization constraint equals 1 ILP constraint. It's almost already in the form that's necessary for ILP. Each of these chains, which was a logical through module link, this big thing, is decomposed into the physical links it's made up of. And each of those physical links, which called P1, P2, whatever, get a variable assigned to them called L of P1, L of P2, and these are the latencies which we want to solve for. These L values are how many registers do I insert on this physical link. So that becomes part of the ILP constraint. The operator that the user specified stays as whatever operator. There's a one-to-one mapping. And the sum of the internal latencies along all these chains is rolled into the right-hand side as the constant. So it's a very straightforward translation between Yes, it works for some reason, between synchronization and ILP constraints. So that's it for synchronization constraints. We ended up with ILP outputs, and we'll stop here for synchronization and go to the separate problem, the pipelining problem. So this is where the meat of the new meat of the talk begins, because this has all been presented before. This is new stuff that's coming. Okay, so automatic pipelining. What's our goal? It's going to be, we're given a maximum by the user, maximum logic depth, Dmax. Logic depth means how many consecutive LUTs are there in a row before a register. Our goal is to ensure that no more than Dmax consecutive LUTs between any two registers exists. So we want to insert registers to make this true. Normally you think of pipeline, you think of increasing megahertz or decreasing nanoseconds. So why did I choose logic depth instead of delay? Well, it's a lot easier for me as a tool maker because I'm not operating in the place and route space. I'm operating in this as a tool that emits Verilog. I have to actually keep characterized database of all of the logic delays through each of my primitives, and that will be a lot bigger of a database if I were to have to redo this for every PBT tech part of process corner. So this becomes more technology independent if I just do logic depth. Also, it's more honest. Let me explain that. So no matter what I do, I can't model interconnect delay effectively. I don't know that. I don't have placement information. I don't. If I were to, instead the user says maximum logic depth equals this. If instead the user said minimum frequency equals this, well, I can't guarantee that because I don't have delays. At least this way I'm being consistent with what the user asks for and what I'm able to provide, instead of basing my megahertz on just logic delays and not interconnect delays. So many reasons why I took this approach. I'll show it's not necessarily always the best, but it's still good enough sometimes. Okay, so I'll now explain the basic concept between how I do the automatic pipelining. So imagine a register to register path somewhere in the interconnect. In the Genie view of things, there exists not raw logic between these. There's structure, there's modules. And each of these has an internal combination logic depth through them. Genie's only able to, by my design restriction, insert registers between modules on these links, so I can't actually pipeline the interior of these. This provides a certain minimum granularity to the pipelining problem. So if the user asked for a maximum logic depth of 3, I'd be dead, because even though technically I could go in here and pipeline it, I can't with this model, because there's a 4 here. I would automatically fail. So that's the constraints under which I'm working. In this world, I have 2 locations where I could insert registers to reduce the maximum combination logic depth, because right now it's like 9, and it could be as low as 4 if I pipeline both of these. Okay, so I'm going to change the picture a little bit. I'm going to remove all the modules and logic. They're still there. This is still combination logic here, but just the picture's a bit different. And I'm going to add a lot more pipelinable locations. I just pretend there is a module between every one of these. It just makes the picture nicer. So here's the approach. Here's an observation. Here's how it all begins. Take some segment of this combinational path that is overweight, meaning on this segment it exceeds the maximum logic depth. We know for sure that we need at least 1 register to go in here, to pipeline it. We don't know if it's just 1 register. It could be 2, it could be 3, but we know it's not 0. So maybe that's not enough. Oh, this happens to be enough. Okay, great. Now it's split into 3 segments that are all underneath the logic depth. Okay, this is the beginning of how I'm going to approach it, but this isn't currently helpful. So instead of just any segment that's overweight, let's instead consider a more conservative segment, smaller, that's something what I call minimally overweight. What this means is, if I were to remove any of the either left or right end caps from this path, it would suddenly become acceptable. So that makes it acceptable, and that makes it acceptable. So in such a minimally overweight segment, I can now guarantee that by inserting 1 register anywhere inside there, it will be successfully pipelined. So I can put it here, 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 and I can guarantee that it will be good. The basic approach for pipelining at least this kind of linear link is I need to find all such minimally overweight segments along this path and create a constraint that says along this segment, add at least 1 register, which in terms of the L variables means number of registers here plus number of registers here plus number of registers here is greater than 0. So the approach to be used then, maybe based on this idea, is we're going to take our interconnect, like physical netlist that we have so far, and create a timing graph from it. We're going to annotate logic debts on this timing graph. We're going to run this algorithm I created called a snake algorithm that does the traversal of the timing graph to find these minimally overweight segments, and for each one, dump an ILP constraint to cause a register to be inserted along it. And then those ILP constraints, just like with synchronization constraints, will all pass to a combined solver at the end to solve both problems together. So we'll go through these steps in order. First, we're going to create a timing graph, and there's a bit to explain here. Two pictures here, top and bottom. On top, we have some physical netlist of the interconnect we have so far in Genie. It's got 4 modules. One user module, something that could be a 2-output split node, and 2 sync user modules. At the bottom, we have the corresponding timing graph. Basically, every inter-module link, that means one that goes between the interfaces of 2 modules, and these are physical links, not logical links. Each of these links, which represents a pipelinable location, gets a vertex inside the timing graph. Actually, every vertex in the timing graph corresponds to a register. Either something that could be maybe be a register or not a register, so a register could go there potentially, or a known fixed register that's inside the core of some module that we can't touch, that's always there for sure. So vertices equals registers, whether present or for sure, or maybe present. Edges in the timing graph get annotated with logic depths, and you can see where they come from with the letters and where they end up with over here. There's 2 sources of logic depths. There's ones that originate from or terminate at these internal registers. For example, for this user module, there's some logic depth A that exists between the register inside and the port, or inside the split node here where there's an internal register and it's related to all 3 ports. There's connections between all of them and they all have their own logic depths. Those get annotated at the bottom. But notice that this one register is replicated 3 times here because we don't actually want to traverse through, we don't want to create a traversal path through this register in the timing graph. All sources and destinations of traversal have to be fixed known registers. There's also purely combinational paths. The blue ones, they're just going from one input to one output without any registers in between. And those get shown here. So that's how we create the timing graph. Next is how do we annotate the logic delays onto it? Where do they come from? So for interconnect modules, Genie actually maintains a pre-characterized database of all of the primitives under many, not all, but many different parameterizations. For each one, store an entry with the logic depths and also the area. So here's an example for Genie split. And this is all created automatically through Rodionov flow. So Quartus is actually run and TimeQuest is run, timing analyzer, to extract these and dump them to a file. So this comes from real stuff of taking each